Hello viewers, in today's session we are going to discuss an important inequality using the concept of Taylor's theorem, right? So let us start. So before proving this inequality, let us quickly see the statement of Taylor's theorem. Now let us consider a function, say y is equal to f of x, which is defined in some interval, the closed interval a comma a plus h. And if this function, it satisfies the condition, that is f of x and its first n minus 1 derivatives are continuous in the closed interval, that is a comma a plus h, and moreover the derivative fnx, it exists for all values of x in the open interval, that is a comma a plus h, then there exists at least one number theta such that theta lies between 0 and 1. Then we have this result, that is f of a plus h is equal to f of a plus h times f prime of a. Then we have h square over factorial 2 f double prime of a up to the nth derivative h raised to n over factorial n, and here we have the nth derivative and we have a plus theta h. Then this statement is known as Taylor's theorem. So this is the statement of the famous Taylor's theorem, which is also known as generalized mean value theorem. So what this theorem says, if we have a function y is equal to f of x, which is defined in some closed interval a comma a plus h, and if f of x and its first n minus 1 derivatives are continuous in the closed interval a comma a plus h, and f and x, it exists for all values of x in the open interval a comma a plus h, then there exists at least one number theta which lies between 0 and 1. Then we have f of a plus h is equal to f of a plus h times f prime of a plus h square over factorial 2h f of double prime of a up to the nth derivative h raised to n divided by factorial n, and here we have fn a plus theta h, right? So this form of Taylor's theorem is known as Lagrange's form of remainder, because this term is known as Lagrange's form of remainder, and sometimes it is denoted by Rn. And here we have the remainder, that is Rn is equal to h raised to n over factorial n fn, and here we have a plus theta h, right? So this is the Lagrange's form of remainder of Taylor's theorem. So now, in order to prove this inequality, we have to slightly modify this statement of Taylor's theorem, right? So let us replace this a by 0, right? And this h by x, and let us write the Taylor's theorem by replacing a by 0 and h by x. So we can now write here that is f of 0 plus x, because a is 0 and h is x, and then we have f of 0 plus h, here we have x for h, and then we have f prime of 0, then we have x square over factorial 2, then we have f double prime of 0 up to the nth derivative, that is x raised to n over factorial n, and here we have f of n, and here we have 0 plus theta x, right? So let us write this statement as f of x 0 plus x is x, f of x is equal to f of 0 plus x times f prime of 0. Then we have x square over factorial 2 f double prime of 0 up to here we have x raised to n over factorial n and f of n, and then here we have theta x. So now we'll apply this result to prove this inequality. So now in this inequality we have cosine x. So let us assume this function f of x as cosine x, right? And let us take the value of n as 2, right? So when we take f of x is equal to cosine x and n is equal to 2, then this statement is now given by f of x, and then we have cos of x because f of x is cos x, and this is equal to f of 0, and then we have x times f prime of 0, and then we have x square over factorial 2, and then we have f double prime, that is the second derivative because we are taking n is equal to 2, so we have x square over factorial 2, and then we have here a double prime, and then here we have theta x, right? So here we have theta x. Okay, so now let us take this equation as equation number 1. So here we are taking the value of n is equal to 2. It implies that we have to consider the derivatives up to a second order, right? So here we have the second order derivative, that is f double prime, and here we have theta. So now here we have assumed that a is equal to 0 and h is equal to x. So we have the interval that is 0 comma 0 plus x, that is equal to 0 comma x. So let us now consider this function f of x is equal to cosine x in this interval, that is 0 comma x, and let us see the properties of cosine function. That is, the cosine function is continuous throughout this interval, that is 0 comma x, for all x belonging to the set of real numbers, right? And moreover, this function f of x is differentiable in the open interval, that is 0 comma x, for all x belonging to the set of real numbers, right? So this implies that f prime of x and f double prime of x exist for all values of x belonging to the set of real numbers, right? And the interval is the open interval, that is 0 comma x. Then there must exist at least one theta that is lying between 0 and 1 such that cos of x is given by this equation. So now we have seen that this function cosine x, it satisfies all the conditions required for Taylor's theorem, right? And moreover, this cosine function is continuous in the given interval, right? So let us find out the derivatives of this function. The first derivative f prime of x is d by dx of cos of x, that is minus sine x. Then the second derivative, because we require only the first derivative and second derivative, and then we have the derivative of minus sine x, that is simply minus cosine x, and it is quite obvious that both the derivatives they exist in the interval that is 0 comma x for all x belonging to R, right? And let us find out the values of f of 0. So f of 0 is given by cos of 0, that is 1. And let us find out the value of f prime of 0 by taking x is equal to 0. Then we have sine 0, that is simply 0. And f double prime of theta x is given by this derivative, that is minus cos, and here we have theta x, right? So let us substitute these values in equation number 1. So we have now f of x is equal to cos x, and f of 0 is 1. Then we have x times f prime of 0, that is simply 0. And then we have x square over factorial 2 is simply 2. And then f double prime of theta x is given by minus cos theta x, right? So now we can write cos of x is equal to 1. Here this term is 0, and here we can take minus x square over 2 and cos theta x. Let us call this as equation number 2. So now, in order to prove this inequality for all x belonging to the set of real numbers, let us form three cases. The case 1 includes only x is equal to 0, right? And case 2 can be taken for all x greater than 0. And case 3 can be taken for all x which are less than 0. So when we take x is equal to 0, x greater than 0, and x less than 0, then we can take care of the entire real number line, right? So let us first consider case number 1 when x is equal to 0. So when we take x is equal to 0 in this inequality, let us see the truth of this, or the validity of this inequality. So when we take cos x is equal to 0 in this inequality, then we have cosine 0 is greater than or equal to 1 minus 0 square over 2, and cos 0 is 1, and here we have 1 minus 0, that is 1 greater than or equal to 1. And this inequality, it suggests that 1 is equal to 1. So this is true, that is for x is equal to 0, this inequality is valid, because we have 1 greater than or equal to 1, and here this equality, that is 1 is equal to 1, is true, right? Now let us consider the case 2 when x is greater than 0. So now when x is greater than 0, let us start with this equation number 2, right? Now here we can see that we have this term, that is cos theta x, and we know that cos of theta x is always less than or equal to 1 for all theta x belonging to the set of real numbers, right? And here we are assuming that x is greater than 0, and we already know that theta is lying between 0 and 1, and x is greater than 0, right? So if we multiply this inequality throughout by x, then the direction of the inequality remains the same, because x is a positive quantity, that is, it is greater than 0. So let us multiply throughout by x. So we have here 0 times x, here we have theta x, and here we have x. So we have here 0 and theta x, and here we have x, right? So when cos of theta x is less than or equal to 1 for theta x belonging to the set of real numbers, when x is greater than 0. So remember, here x is greater than 0. So now if we multiply this inequality both sides by minus x square over 2, because here we have minus x square over 2. So this inequality gives us minus x square over 2, and here we have cos theta x, and the direction of the inequality get reversed because we are multiplying both sides by a negative number because x square is positive, right? So we have greater than or equal to minus x square over 2 times 1, right? Okay, so now let us add 1 both sides. So we have 1 minus x square over 2 cos of theta x, and here greater than or equal to minus x square over 2, right? And since we are adding 1 to both sides, so here we have plus 1, right? And this expression is equal to cos of x. So we can now write cos of x is greater than or equal to 1 minus, we can write 1, then we have minus x square by 2. So cos x is greater than or equal to 1 minus x square by 2, which is the required or desired inequality. So now consider the third case when x is less than 0, that is x is a negative quantity, right? So when x is less than 0, then if we multiply both sides by minus 1, then we have minus x, and the direction of the inequality get reversed. So we have minus x greater than 0, right? So this is an important step while dealing with case 3. So in case 3 we are assuming that x is less than 0. So when x is less than 0, and if we multiply both sides by a minus 1, then minus x is greater than 0. Now let us substitute y is equal to minus x. So if we take y is equal to minus x, then this inequality gives us y is greater than 0, right? See, this is an important step here. Minus x is greater than 0, and we are taking y is equal to minus x. So substituting minus x as y is greater than 0, right? So when y is greater than 0, then from case number 2 we can write cos of y is greater than or equal to 1 minus y square by 2, because y greater than 0 implies y is a positive number, and when y is a positive number, we have just proved in case 2 that when x is greater than 0, then cos of x is greater than or equal to 1 minus x square by 2. That is, when x is a positive quantity, x is greater than 0, then this inequality is a valid one, right? So when y is greater than 0, then replacing this x by y, that is for positive y, cos of y must be greater than or equal to 1 minus y square over 2. Now let us once again replace this y by minus x. So we have cos of minus x, and then we have 1 minus x square over 2, right? So cos of minus x, from trigonometry we know that cos of minus x is equal to positive cos of x, right? So cos of minus x is simply equal to cos of x, and this is greater than or equal to 1 minus x square is positive x square, so we have x square over 2, and this is our required inequality for all x less than 0. So viewers, this is how, with the help of these three cases, that is in the case 1 we have x is equal to 0, in the case 2 we have x greater than 0, and in case 3 we have x less than 0. So in all these situations this inequality is valid, right? So we can say that cos of x is greater than or equal to 1 minus x square over 2 for all real numbers, that is for all x belonging to the set of real numbers. So this is how, by the application of Taylor's theorem, we can arrive at this inequality.